somewhere in the universe, everything you can ever observe simply stops, not because space ends, not because nothing exists beyond it, but because the universe refuses to show you more. Every deep image of space ends at this same invisible boundary. And the unsettling part is this: it isn't a failure of technology, and it isn't something we'll overcome with time. It is built into the way reality works. Tonight, we follow that boundary to its source, to understand what scientists really mean by the edge of the universe, why it exists, and what lies beyond the farthest thing we will ever see. Before we follow that boundary, if you find value in these deep space videos, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. There's a certain kind of question that sounds simple until it starts to deform in our hands. What lies beyond the edge of the universe? We can almost picture it, like the edge of an ocean, a final line, a last shoreline, a boundary where existence stops and something else begins. But the universe doesn't behave like an ocean. It doesn't give us a coastline. It gives us something colder and far more unsettling. Because the closest thing we have to an edge is not a wall in space. It's a limit inside our vision, a limit written into light itself. And once we understand that, the question changes. Quietly, completely. Not what is out there, but what can ever reach us, and what can never, no matter how long we wait. Everything we know, every galaxy photographed, every nebula mapped, every star counted, comes to us the same way, not by reaching outward, but by receiving something that already left: light. A photon is a small thing, weightless, silent, without memory, and yet it carries the history of everything it has touched. When a star explodes, we don't hear it, we don't feel the heat, we receive a faint signal, sometimes after the fact, sometimes long after the civilization that watched it has already vanished into dust. And this is the first uncomfortable truth. We do not see the universe as it is. We see the universe as it was. Even the moon isn't now. Its light takes a little over 1 second to reach us. The sun is about 8 minutes in the past. And beyond that, the delay becomes monstrous. The night sky is not a window. It's an archive, a museum of ancient light. Imagine this. Picture yourself standing alone on a perfectly dark beach at night. Far out over the ocean, scattered boats are turning on their lights, one by one, at different distances. The nearest ones brighten your face immediately. But the farther boats, their light arrives late, faint, delayed by the distance, and eventually out there. In the black, you reach a point where the ocean is still full of boats, but their lights simply haven't reached you yet. Not because the boats aren't real, not because the ocean ends, but because light has a travel time. That boundary, where the ocean continues but the light doesn't reach you yet, is the closest everyday feeling we have to what cosmologists call the observable universe. It's not the whole ocean, it's the part whose light has arrived. Light moves fast, so fast that our instincts fail to hold it. In 1 second, light circles Earth more than 7 times. In the time it takes you to blink, light has already crossed continents. And yet, even that speed has limits. Even the fastest thing we know still needs time, and time is the universe's strictest gatekeeper. Because the universe has a finite age, about 13.8 billion years, which means the oldest light we can receive has been traveling for at most that long. So the observable universe is defined by a simple rule. It contains everything whose light has had enough time to reach us since the beginning. That's it. No walls, no borders, no cosmic fence. Just the distance light can cross in the lifetime of the cosmos, in an expanding universe. And that expansion changes everything. This is where the universe becomes almost philosophical. When we look outward, we aren't just looking across space, we are looking across time, A galaxy 1 billion light years away is seen as it was 1 billion years ago, before many of Earth's multicellular animals ever existed. So every telescope is a time machine, not metaphorically, literally. NASA's space telescopes, the Hubble Space Telescope, and the James Webb Space Telescope, built by NASA, ESA, and CSA, don't just magnify, they rewind. They collect photons that began their journey before human beings existed, before the first cities, before the first oceans look the way they do now. And the farther we push, the more the universe starts to look unfamiliar. Galaxies become smaller, more chaotic, more raw, as if we are watching the cosmos grow up. But then a disturbing realization arrives. If distance is time, then there must be a farthest time, a limit, a point beyond which the light simply hasn't had enough life to arrive. Not darkness, not emptiness, just not enough time. Now comes a trap our minds fall into almost automatically. If the observable universe is everything we can see, we imagine a sphere around Earth, and we start to picture Earth as the center. But Earth is not the center, not of the universe, not even of the Milky Way. The observable universe is a sphere centered on the observer, only because observation is personal. If we were standing in a galaxy 10 billion light years away, the observable universe would still be a sphere, but centered on that place. Different sky, different ancient light, different edge. So the universe does something strange. It gives every observer their own horizon, their own visible domain, their own cosmic bubble of information. And that means the word edge is already misleading, because there isn't one edge. There are as many edges as there are places that can observe. This isn't a universe with a center. It's a universe where every conscious point can feel like a center, because light arrives from all directions. And yet, none of those centers are fundamental. They're just perspective. Here is one of the most staggering measured facts in modern cosmology. The observable universe is about 93 billion light years across, not 13.8 billion. Not even close. About 93 billion light years in diameter. That number lands like a contradiction. How can something only 13.8 billion years old have a diameter so much larger than 27.6 billion light years? It sounds like the universe is violating its own speed limit. But it isn't. What's happening is subtler and more unsettling, because space itself has been expanding while the light was traveling. The photons didn't cross a static map. They crossed a map that kept stretching under them, like trying to reach a distant friend by walking across a rubber floor that's slowly being pulled apart. You still move forward, but the distance you're trying to cross keeps changing. So when cosmologists say 93 billion light years, they are talking about the distance now, the current separation between us and the most distant regions whose light has reached us. That light began its journey much closer, but the universe expanded around it, and the distance inflated into something far larger than our instincts can accept. A light year is already a brutal unit. It's the distance light travels in 1 year, nearly 9.46 trillion kilometers, about 5.88 trillion miles. Now take 93 billion of those. The number becomes so large it stops behaving like meaning. So let's compress it into something human. If we could travel at the speed of light, and we can't, not even close, crossing the observable universe would still take 93 billion years. That's more than 6 times the current age of the universe. Even if a journey like that had begun when the first pyramids rose in ancient Egypt, you wouldn't even have moved 1/10,000,000th of the way across. Even if it began when the first humans painted cave walls, your progress would still be invisible on that scale. The observable universe is not big in the way a desert is big. It's big in a way that breaks the idea of travel itself. When we say the universe is expanding, we're not saying galaxies are exploding outward into empty space like shrapnel. We're saying the space between large structures increases over time. This is the part where everyday language collapses, Because in daily life, space is a stage. In cosmology, space is an actor, and it moves. This expansion is not a guess, it's measured. Astronomers observe that distant galaxies' light is stretched, shifted toward redder wavelengths, because the space it travels through expands. The farther the galaxy, the greater the shift. This pattern is seen across the sky. It is one of the foundational observations of modern cosmology, and it means the observable universe is not simply how far light can go, it's how far light can go through an expanding reality. So as the universe expands, something strange happens. The boundary of what we can see is not fixed like a circle on a map. It evolves, it breathes, it changes with time. And our number, 93 billion light years, is not a boundary in the sense of an end. It is a measurement of the farthest information currently available to us in the present cosmic moment. Here's where the story starts to tighten. Because this visible universe, this 93 billion light-year wide sphere, is already overwhelming. Hundreds of billions of galaxies, each with billions of stars, each star potentially surrounded by worlds, a scale so vast that the human brain begins to protect itself by turning it into abstraction. But then the universe delivers a quiet punch. This is not the entire universe. This is only the portion whose light has reached us, only the illuminated bubble, only the region we can confirm with photons that actually arrived. Outside it, there is no evidence of a wall, no evidence of an ending, just distance we have not received information from. And the unsettling part is that this is not philosophical, it's mechanical. If light has a finite speed and time has a finite length, then there must be regions still beyond our reach, regions whose light has not had enough time to arrive, not because they are forbidden, but because the universe is old, yet not infinitely old, and that creates a tension that never fully resolves. The universe may be far larger than what we can see, it may be infinite, or it may be finite in a way our intuition can't picture, but we can't claim what we can't test. We can only say, with scientific honesty, the observable universe is the part that has had time to make contact with us. Everything beyond is, for now, outside our evidence. And if you really let that sink in, you realize something almost haunting. You are not looking at the whole universe. You are standing inside a bubble of visibility, an information sphere, carved out by light speed and cosmic time. The sky feels infinite because our senses were never built for this scale. Our eyes see stars as pinpricks. Our minds compress billions of years into a sentence. We evolve to read faces, follow footsteps, and survive winters, not to comprehend a horizon 93 billion light years wide. And yet, here we are, a species that can measure the size of its own visible cosmos. A species that can look into the past simply by lifting its gaze. That fact alone should feel impossible. So when we ask, what lies beyond the edge of the universe, we're really brushing against a sharper truth. The edge isn't where space ends, it's where our information ends, where our evidence ends, where the light has not yet arrived. But then, another problem appears. Because if everything we can know comes to us by light, and light must travel through an expanding universe, then visibility itself becomes a kind of journey, a long, brutal pilgrimage across time, across stretching space, across distances that do not sit still. And that raises the next question, one that scientists return to again and again because it defines everything we can ever observe. Why does the universe have a horizon at all? Why does time create a boundary? Why are there regions that have never been able to speak to us, not even once, not even with a single photon? Because the closer we look at that limit, the more it starts to feel less like a measurement and more like a law written in the oldest travel story in existence, the journey of light itself. Light is not just illumination. Light is a messenger that can bleed for billions of years across a universe that refuses to sit still. And the moment we accept that, we begin to understand why the sky has a limit. Not a limit in space, a limit in arrival. Because every photon we catch tonight, every faint glimmer from a distant galaxy, is the end of a journey that began long before Earth had forests, long before the first animals walked on land, long before our species had a name. But then something unsettling follows. If light must travel, and if the universe has a finite age, then there are places whose light is still on the way, and there are places whose light will never arrive at all. That is not poetry. That is physics. We can describe the observable universe in one sentence that sounds almost too simple to be true. We can only see what has had time to send us a signal. That's it. Not what is bright enough, not what is close enough, what has had time, and time is ruthless. The universe is about 13.8 billion years old. That means there is a maximum travel time for light. A cosmic clock started near the beginning, and everything we see is filtered through that clock. Even if something exists right now beyond a certain distance, we can't see it yet, because its light hasn't reached us. And that creates what scientists call a horizon, a boundary of visibility created not by darkness, but by the simple fact that the universe has not been around forever. This is where the story cracks open. Because horizon sounds like a line in space, but the real horizon is a line in time. Imagine this. Picture a vast city during a power outage, seen from a hill. In the distance, generators begin to restore power, one neighborhood at a time. Streetlights flare on in patches, windows glow, whole districts wake up. But far out, the city continues, silent and unlit. Not because it doesn't exist, but because electricity hasn't reached it yet. Now replace electricity with light, replace the city with the universe, replace the repair crew with time itself. That is what our sky is like. We are not looking at everything. We are looking at the regions that have already been switched on, regions whose light has had enough time to cross the cosmic distance and reach our eyes. This is where intuition starts to fail us. We tend to imagine space as a fixed stage and light as a runner crossing it. But the universe has an age limit, and the runner can only run for so long. If a galaxy is so distant that its light would need more than 13.8 billion years to reach us, then no matter how powerful our telescope is, no matter what NASA builds, no matter what ESA launches, there is nothing to receive. Not yet. And in some cases, not ever. Because the universe is not just old, it is expanding, and that expansion means the finish line isn't standing still. So there exist regions so distant, so separated by the stretching of space, that they have never been in contact with us, not once, since the beginning. No shared signals, no exchanged light, no causal handshake. They could be full of galaxies, they could be empty. But right now, the truth is colder. If their information hasn't reached us, we do not get to claim we know. Science is disciplined that way. When we stare into a black sky, it's natural to feel that darkness means emptiness. But the universe's dark is often just unarrived. Time is the curtain, not night. The deeper we look, the more we are watching a universe that is younger. We are catching galaxies in their earlier forms. We are seeing light that left when the cosmos was still assembling its first grand structures. And that means our view is always delayed, always historical, always incomplete. This should be impossible for the human mind to accept. We live in the present, but the cosmos forces us to live visually inside the past. Astronomers have a name for this delay. They call it look-back time. Look-back time is simply how far into the past we are seeing when we observe something far away. It sounds clinical, but it describes something almost haunting. When we look at a galaxy billions of light years away, we are not just measuring distance, we are receiving a memory. A message that left when Earth was different, when the continents were arranged differently, when our ancestors were not even close to existing, and if that look-back time goes far enough, we reach eras when Earth itself had not formed, when the sun was not yet a star, when the atoms that would become our bodies were still being forged inside earlier generations of stars. That's the emotional gravity hidden inside a technical term. Look-back time is the universe forcing us to admit we cannot observe reality without also observing history. But then the story becomes even stranger, because when we say a galaxy is billions of light years away, that phrase can quietly lie to us if we imagine the universe as a static grid. The universe is expanding. So, when a photon began its trip toward us, the galaxy that emitted it was closer than it is now. The light didn't travel through a frozen landscape. It traveled through space that kept stretching while the photon was already in flight. So there are two different distances we have to hold in our hands at once. The distance when the light was emitted, and the distance now, after billions of years of expansion. That difference matters, because it's part of why our observable universe is so enormous in today's measurements. It's also part of why the concept of an edge becomes slippery, because what we are really mapping is not just distance, but a relationship between distance and time inside an expanding cosmos. Here's one way to feel this without equations. Think of a friend who moved away years ago. You mailed them a handwritten letter, ink, on paper, a physical message. But while your letter was travelling, your friend kept moving farther. By the time the letter arrived, the address was no longer where they are now. It was where they were then. And yet the letter still arrived. It still carried truth. Just truth from a different time. That is what light does. Every photon is a letter. Every galaxy is an address that has changed. And the universe is the postal system, expanding, stretching routes, changing distances even as the message moves. So when we see a distant galaxy, we are not seeing it over there. We are seeing it back then. And the farther we look, the more brutal the delay becomes. Now comes the quiet contradiction that cosmologists live with. When we say we can see something, we mean the light has arrived. But arrival doesn't guarantee completeness, because the universe has been around for 13.8 billion years, but it has not been around long enough for every region to exchange signals with every other region. So the observable universe isn't the universe. It's the part of the universe that has intersected with our past light cone, our history of received information. That phrase sounds technical, but the meaning is simple. We only know what has had time to reach us, and the rest is beyond evidence, not beyond existence, beyond contact. And that creates a deeper mystery. If the universe is enormous and ancient and full of light, then why do we not see everything? Why is the cosmos not fully connected? Why does the universe allow islands of reality that cannot speak to each other? And if you want to feel how strange this is, hold your hand up in front of your face. You can see your skin because light from the room reaches your eyes instantly, practically without delay. Now imagine a version of reality where the room is so large that light takes years to cross it. Imagine living in a world where seeing your own surroundings meant seeing them in the past. That is what you are doing every time you look into space. You are not just looking outward. You are looking into a delayed universe, into an archive built by light travel time and cosmic expansion. And suddenly the word horizon stops sounding like a metaphor. It becomes a boundary that you can almost feel in your bones. There are places that could exist right now, yet remain unseen, not because they are hidden, but because the universe is not old enough for their light to arrive. This is the most important shift we can make. We have to stop thinking of the cosmos like a landscape fading into night. The edge is not where light fails, it's where time fails, where the universe has not had enough lifetime to connect us to more distant events. Even the most powerful telescope cannot reach beyond that, because telescopes don't reach out and grab light. They wait, they collect, they receive. And if no photon has had time to arrive from a region, then the telescope receives nothing, not because of weakness, but because of the universe's timeline. This is why scientists hate mysteries like what's beyond the edge when it's framed as a place, because the real edge isn't a location, it's a causal limit, a limit written into the speed of light and the age of the cosmos. So the horizon is not an object, it is not a wall, it is not a border where space ends, it is a law about what can influence what, a law about contact. It tells us something both humbling and powerful. No matter how intelligent we become, no matter how far our machines travel, the universe itself decides which regions can ever exchange information with us. The sky is not infinite to us. It is finite because the universe has a history, and we are trapped inside the portion of that history that has had time to reach our eyes. But then, a sharper question rises, because if our visibility has a limit, what exactly is that limit? How do cosmologists define it with precision? How does it change as the universe ages? And why does the word horizon carry more weight than it seems? Because once we name that boundary clearly, once we define it as more than a feeling, the idea of an edge becomes even more disturbing and even more real, not as a place we could travel to, but as the farthest boundary of causal connection itself. And that is where the universe's true horizon begins to take shape. There's a moment in cosmology where the question stops being emotional and becomes surgical. If our view ends because light has a finite travel time, then the universe doesn't just have a limit in a casual sense, it has a defined boundary of reach, a boundary we can name, a boundary we can calculate, a boundary that doesn't care what we want to be true. And this is where the story becomes more disturbing, because the universe's true edge is not where space stops. It's where cause and effect stop being able to touch us. Cosmologists have a name for the farthest distance from which any signal could have reached us since the beginning. They call it the particle horizon. The name is clinical, almost cold. But the meaning is profound. It is the maximum range of cosmic contact, the farthest radius from which light, moving at the fastest speed allowed by physics, could have travelled through the expanding universe and arrived here by now. Everything inside that. Range is, in principle, part of our causal past. Everything outside it has not had time to reach us, not with light, not with gravity, not with any influence that travels at or below light speed. That boundary is not a wall, it is not an edge you could crash into, it is a limit written into time itself. And it is the closest thing we have to a real cosmic border. Our minds want a simple picture, a sphere like a bubble floating in emptiness, an edge you could fly toward, a final line that separates universe from not universe. But the particle horizon is not a structure. It doesn't exist as a physical shell in space. If we could travel outward, far beyond what any human technology could survive, we would not encounter a boundary you could touch. There would be no seam in the darkness, no final curtain, no cosmic fence. The horizon is not an object sitting out there. It is a statement about what has had time to happen, about what has had time to affect us. It's not a place. It's a limit on connection, and that's why it feels so unsettling, because it suggests something our instincts resist. Reality can exist beyond our ability to be influenced by it. Imagine this. Picture a massive city during a blackout and a storm moving through it. You're standing on a rooftop and you shout a name. At first, your voice travels easily. Nearby rooftops hear you. A few blocks away, someone turns their head. But the storm eats sound. Wind tears it apart. Distance thins it. Noise smothers it. At some point, the city continues, but your voice cannot reach any farther. Not because the buildings end, not because the city ends, but because there is a limit to propagation through a harsh environment. Now swap sound for light, swap wind and noise for the expanding fabric of space. The particle horizon is the farthest rooftop whose signal could have reached us since the universe began. Beyond that, the universe may continue, vast, real, structured, but there has not been enough time for its message to arrive. Now comes the strange part. We often talk about the observable universe as if it's fixed, but the particle horizon is not frozen. It changes because time keeps moving. Every year that passes is another year for light and for any influence to travel. So as the universe ages, the particle horizon grows. More time means more reachable distance. More reachable distance means more of the universe becomes, in principle, observable. But then we have to hold two truths at once. Yes, the horizon grows with time. However, the universe is also expanding while that time passes. So the boundary of contact grows, but it grows through a universe that is stretching under it. That's why the distances we use in cosmology can feel like they contradict everyday logic. It's also why the visible universe can be far larger in today's measurements than a simple speed of light times age intuition would suggest. Because the horizon is not a circle drawn on a static map. It is a boundary traced through a moving, breathing cosmos. There's another twist that quietly destroys the last remnants of the edge idea. The particle horizon is centered on the observer, not because the observer is special, but because observation always begins at a location. If we were standing in another galaxy, far across the cosmic web, that place would have its own particle horizon, its own sphere of causal contact, its own visible history. They would see ancient light we will never see, and we see ancient light they will never see. Two observers can live in the same universe and possess different skies, different pasts, different boundaries of contact. And that leads to a deeply uncomfortable implication. There is no single, universal edge shared by everyone. The edge is a relationship between a location and the universe's timeline. So the universe does something almost paradoxical. It gives every observer a horizon, while refusing to give the universe an edge. To understand why this matters, we have to let go of a comforting assumption. We assume that if something exists, it should be able to affect us eventually. But physics does not promise that. Physics promises something harsher. Information cannot travel faster than light. That includes signals, matter, and the influence of gravity. Einstein's general relativity doesn't just describe how objects move, it describes how cause and effect are stitched into space-time. So the particle horizon is not merely about what we can see, it is about what can ever be in our causal past up to this moment. It is the boundary of all possible cosmic messages that could have reached us since the beginning. And inside that boundary lies everything we have evidence for. Outside it lies, not necessarily mystery, but lack of contact, a silence not made of emptiness, a silence made of time. And if you want to feel how radical this is, think about what it means for you, right now, to exist in a universe with a causal boundary. You are standing inside a region of space that has been able to exchange signals with you since the cosmic beginning. Every star you see with your naked eyes, every faint galaxy a telescope collects, belongs to the portion of reality that has been able to reach you. But beyond that, there may be galaxies whose light has never touched Earth. Not once, not even a single photon, and your senses were never built to recognize that as real. Your eyes interpret unseen as absent. Your instincts interpret distant as reachable, given enough time. But the universe refuses both of those comforts. It allows reality beyond contact. So why do we keep using the word edge at all? Because it captures an emotional truth, even while it distorts the physical one. An edge implies a boundary you could approach, a final place, a last line. The particle horizon is not that, and yet it behaves like an edge in one way that matters deeply. It divides what can be connected to us from what cannot yet. It marks the end of evidence, the end of direct access, the end of the story we can verify with arriving information. That is why edge is misleading, but it is also why it is powerful, because it forces us to confront a universe that is not obliged to be fully knowable from any single location. Now, the story sharpens into a paradox that scientists take seriously because it lives inside real data. We look in opposite directions across the sky and we see a universe that is remarkably similar on the largest scales. Patterns repeat. The cosmos looks broadly uniform. That observation is one of the foundations of modern cosmology. But then the horizon reminds us of something uncomfortable. In the early universe, many regions were so far apart that they should not have been able to exchange information yet. Not enough time, not enough causal contact. So how did the universe end up so coordinated on large scales? How did distant regions end up sharing such similar conditions? This is not a philosophical trick. It's a real tension between what horizons imply and what observations suggest. And it tells us something important about how seriously scientists treat these boundaries. Horizons are not just language. They shape the questions that define cosmology. So the particle horizon becomes a kind of cosmic truth we can't escape. It is the radius of everything that could have influenced us since the beginning. It is not a wall in space. It is not a physical edge. It is a moving boundary of possible contact. And it is centered on us, only because we are the ones doing the receiving. But then, one more unsettling realization emerges. If every observer has their own horizon, if every location can claim a center of visibility, then what does it mean to talk about the universe expanding at all? Expanding away from what? Away from where? If we are not at the center, and no one is, then how can the cosmos grow larger in every direction, from every point, without breaking logic? Because this is where the story becomes almost impossible to picture. A universe that expands everywhere. A universe where every observer feels like the center. A universe where edge is only a limit of contact, never a boundary of existence. And once we step into that idea, the last human intuition collapses. The need for a center, the need for an outside, the need for space to behave like a room. Because the next truth is colder and far more cinematic. The universe doesn't expand into anything. It expands as space itself. There's a kind of retreat that feels personal. You walk toward someone and they step away. You speed up and they keep drifting back. It feels like the universe is doing that to us. Because when we look outward, nearly everything is moving away. Galaxies in every direction, retreating, redshifting, slipping into distance like boats pushed by a silent current. At first, it sounds simple. Things are flying outward from a center, like an explosion. But then, the data refuses that comfort, because wherever we stand, here or in some galaxy billions of light years away, we would see the same pattern. Everything would still be moving away, in every direction, from every place. And that should be impossible, unless the thing expanding isn't the matter, unless it's the stage itself. Our instincts imagine galaxies as objects moving through a pre-existing emptiness, like sparks thrown from a firework. But that mental image breaks almost immediately. Astronomers measure the light from distant galaxies and find a pattern so consistent it became one of the pillars of modern cosmology. The farther away a galaxy is, the faster it appears to be receding. This relationship, first observed in the early 20th century, building on measurements by astronomers like Vesto Slipher and later framed through Edwin Hubble's work, doesn't look like random motion. It looks like a law, a rule written into distance itself. But then comes the deeper twist. In Einstein's general relativity, space isn't a passive container. Space has geometry, And that geometry can evolve. So when cosmologists say the universe expands, they don't mean galaxies are simply traveling through space. They mean the space between galaxies is increasing. The distances are growing because the metric, the scale of the cosmos, is changing. It's a subtle difference, and it changes everything because it removes the need for a center. Here's the disturbing part. If this were a normal explosion, there would be a special point, the origin, a center from which everything flies outward. But in cosmic expansion, every observer can measure the same retreat. Wherever we are, we see galaxies receding, and observers elsewhere would also see galaxies receding from them. Not because they're special, because the expansion is happening everywhere. It's not things moving away from us. It's distances increasing between everything that isn't gravitationally bound. That phrase can sound dry, so let's make it real. Our Milky Way and the Andromeda Galaxy are gravitationally bound, locked in a slow dance that will eventually become a merger. Local gravity can resist expansion, but beyond local groups, on the largest scales, the universe behaves differently. On the largest scales, the distances between clusters of galaxies grow with time, not because the clusters fire rockets, because the space between them stretches. And that is why the recession pattern looks the same from any location, because the rule is embedded in the fabric, not in the objects. Imagine this. Take a plain shirt and draw a few dots on it with a marker. Now stretch the shirt outward with your hands. None of the dots are crawling across the fabric. They don't have legs. They aren't moving through the material. But every dot becomes farther from every other dot. From the perspective of any single dot, all the others are receding, and the ones that start farther away separate faster, because there's more fabric between them that can stretch. That's expansion in the simplest physical sense our hands can understand. But this is where the analogy can betray us, if we aren't careful. Because a shirt stretches into the air around it. It has an outside. The universe does not need an outside. The universe does not need to expand into anything. In general relativity, expansion is a change in the distances defined inside spacetime itself. No external room required. No cosmic air, no surrounding emptiness, just geometry evolving. And that is the first time our intuition starts to fracture. Cosmologists often use a balloon to explain this. Imagine a balloon with raisins stuck to its surface. As the balloon inflates, every raisin sees every other raisin move away. No raisin is the center of the surface. No raisin is special. The center of the expansion is not on the surface at all. This is a powerful image, but it has limitations we have to respect. A balloon has a center in the room. A balloon expands into surrounding space. The universe doesn't have to. Also, the balloon's surface is two-dimensional, while our universe has 3 dimensions of space. So, the balloon is not the universe. It's a shadow of an idea, a way to train the brain to stop searching for a central point. The real lesson is this: expansion can be uniform without implying a center inside the expanding space. And once we accept that, the question, where is the center, collapses. There isn't one, not inside the space we inhabit. So how do we know expansion is real? We can't hold space-time in our hands. We can't watch the universe like a balloon from the outside. We infer expansion by watching what expansion does to light. When light travels across the universe, its wavelength is stretched along with the space it moves through. That stretching shifts the light toward the red end of the spectrum. Redshift. It's a signature written into photons. Subtle, measurable, repeatable. This is why huge observatories matter. This is why teams using NASA missions and ground-based telescopes map galaxies by the millions. This is why ESA missions and large surveys keep refining the cosmic distance ladder. They aren't just looking at pretty spirals, they are measuring the universe's geometry in motion, and here, numbers begin to matter. Astronomers describe the expansion rate with a value called the Hubble constant, often spoken as the Hubble constant, or sometimes H0. It's commonly quoted as around 70 kilometers per second per megaparsec, give or take, depending on the method. That unit sounds like a spell, so let's translate it into something we can feel. A megaparsec is about 3.26 million light years. So, on average, for every additional 3.26 million light years of distance, the recession speed increases by about 70 kilometers per second, about 43 miles per second. That means distance itself carries a built-in scaling of separation. And there's another twist. Different measurement methods don't perfectly agree on the exact number, a tension modern cosmology is still wrestling with. Even here, where the universe seems to hand us a clean rule, there's still friction, still mystery, and this is where you can feel the trap of being human. Because if everything is receding from us, it feels like we are central. It feels like the cosmos is arranged around our position. But that feeling is an illusion created by perspective. We are not sitting at the universe's hub. We are simply located inside space-time, receiving light that has been stretched on its way to us. If we were standing on a planet in a galaxy 10 billion light-years away, we would still feel like the center of a cosmic retreat. We would still watch the sky peel outward in every direction, and we would still be wrong to think we were special. The universe is not honoring us, it is obeying geometry. This is where Einstein's work becomes more than historical. General relativity is not just a theory of gravity, it is a theory of space-time itself, how matter and energy shape it, and how that shape guides motion. In this framework, the expansion of the universe is not a force pushing galaxies outward. It is a feature of the solutions to Einstein's equations for a universe that is, on large scales, uniform. That uniformity, what cosmologists call homogeneity and isotropy, isn't a philosophical wish. It's an observational conclusion from large surveys of galaxies and the large-scale structure. So, in a universe that is, on average, the same everywhere and in every direction, general relativity naturally allows a changing scale factor, a changing cosmic ruler. Our ruler gets longer, our grid stretches, not because the universe is flying into a void, but because the definition of distance evolves. And when our definition of distance evolves, the universe can be expanding without any external space. That concept is not just counterintuitive, it's almost violent to the mind, because it removes the last familiar anchor, the idea of a background room in which everything happens. Once we stop demanding a center, the next instinctive question arrives. If it's expanding, what is it expanding into? And the most honest answer is, it doesn't have to expand into anything. That question assumes space is embedded in a larger space. But in general relativity, space-time is the structure, the arena, the full geometry we are describing. Asking what it expands into can be like asking what the surface of Earth expands into when you walk east. You don't need an outside direction to move across a curved surface. You just move. The geometry is self-contained. Again, the Earth analogy has limits. Earth's surface is embedded in three-dimensional space. But the key lesson remains. A space can be finite without edges, or infinite without boundaries. Those are different possibilities, and both can exist without contradiction. We tend to confuse finite with has an edge, but those are not the same. A finite universe could be curved back on itself in a way that has no boundary, like a three-dimensional version of a sphere's surface. You could travel forever and never find a wall, never find a border, just geometry that loops. An infinite universe, on the other hand, has no total size at all, no outer boundary, because there is no outermost region. In both cases, expansion still makes sense, because expansion isn't about crossing a border, it's about the internal distances changing with time. So the universe can be expanding and still have no edge, or expanding and be infinite. That is why cosmology feels like a philosophy written in measurements, because our language keeps trying to drag the universe back into familiar rooms and boxes, and the universe keeps refusing. Here is the deeper conflict that sits beneath everything we've said. If expansion is the stretching of space itself, then distance is not just separation. Distance becomes dynamic, a moving target, and that means our most basic assumptions about travel and reach begin to fracture. If we aim a spacecraft toward a far galaxy, we imagine the distance is fixed and we can slowly close it. But in an expanding universe, the space between us and that galaxy can increase while we travel. This doesn't mean expansion prevents all motion. Locally, gravity and motion behave as expected. We can reach planets, we can cross the solar system, we can leave our star. But on the grandest scales, the universe introduces a new kind of separation, one built not from speed, but from geometry. And that creates a bigger problem, because our minds want a simple question: how far can we go? But expansion forces a harder one: how far can we remain connected? So the universe expands everywhere, not outward from a center, not into an outside, everywhere. The cosmos grows by stretching its own definition of distance, which means the edge we imagine is not a physical boundary. It is a limit created by time, light speed, and an expanding geometry. But then comes one last, quieter consequence. If expansion stretches space, then the oldest light we can see is not just old, it is distorted by the universe's growth, stretched thinner, cooled, transformed into something almost ghostly, a relic signal that fills the entire sky, arriving from every direction like a frozen echo. And once we realize that such a signal exists, we realize our telescopes are not just looking at galaxies, they are looking toward a final, ancient surface of light, a boundary not of space, but of visibility itself. Because somewhere out there, everywhere out there, there is a glow so old, so evenly spread, so primordial, that it becomes the farthest light we can ever receive. There is a point where our telescopes stop, not because we lack power, but because the universe itself refuses to let light carry us any farther. We can build mirrors bigger than houses. We can place observatories above Earth's atmosphere. We can tune our instruments to faint infrared whispers and ancient radio signals. But eventually, every electromagnetic road ends at the same place. Not a wall, not an edge in space, a surface in time, a pale, omnipresent glow that fills the entire sky, quiet as ash, ancient as the first breath of the cosmos, the CMB, the cosmic microwave background. And once we understand what it is, we realize something unsettling. The farthest thing we can see is not a galaxy. It is the universe itself, when it was still young enough to be almost unrecognizable. We tend to think the oldest light would be tied to the oldest stars, but the CMB is older than stars, older than galaxies, older than any structured thing we'd recognize as astronomy. It is light released when the universe was still a hot, dense ocean of particles and radiation, so energetic, so violent, that atoms could not survive. In that early time, space wasn't empty. It was filled, not with calm darkness, but with a kind of blinding, scorching fog, a universe where light could not travel freely. Because everywhere a photon tried to go, it was immediately scattered, bounced, redirected, trapped by charged particles. The cosmos was like a storm of firelight that couldn't escape its own chaos. And then, slowly, it changed. Not by choice, by cooling, by expansion, by time doing what it always does. Imagine this. Picture a small room filled with thick smoke. A bright lamp is on in the center. You know the light is there. But the smoke is so dense that you can't see across the room. Every beam is scattered. Every ray breaks apart and dissolves. Now imagine the smoke slowly thinning. Minute by minute the air clears, and suddenly at a specific moment, the room crosses a threshold. You can see. Not because the lamp changed, because the air changed. That is what happened to the universe. For hundreds of thousands of years the cosmos was opaque, like a sealed fog of plasma, and then, at a particular moment, it became transparent, and the light that was trapped inside finally escaped. That escaped light is the CMB. The universe began incredibly hot, so hot that matter couldn't form stable atoms. Electrons and atomic nuclei couldn't stay bound together. Everything was stripped apart, a sea of free electrons and nuclei bathed in radiation. And in that environment, light couldn't go far without being scattered. Every attempt to travel became a collision. So the early universe wasn't dark, it was too bright to see through. But expansion changes temperature. As space expands, the universe cools. And after roughly 380,000 years, the cosmos cooled enough for electrons to finally settle into stable orbits around nuclei. Hydrogen atoms formed. This event is called recombination, a name that sounds like something tidy and administrative, even though it marks one of the greatest turning points in cosmic history. Because the moment neutral atoms formed, the universe changed its behavior. Free electrons had been the main reason photons couldn't travel. Remove most of those free electrons, and suddenly the universe becomes transparent. Light stops being trapped. Photons decouple from matter. They begin traveling in long, straight journeys across the expanding cosmos. The CMB is the relic of that moment. It is the oldest light we can ever receive, because it is the earliest time the universe allowed light to travel freely. This is where our question about the edge takes a sharp, physical form. When we look outward with any telescope, no matter the wavelength, we eventually run into this boundary. Not because there's nothing earlier, but because earlier than recombination, the universe was opaque to light. Before the CMB, the cosmos was like that smoke-filled room. Photons existed, yes, but they were trapped in constant scattering. No clean line of sight, no image could survive the journey. So the CMB becomes a kind of visible limit, not the limit of existence, the limit of electromagnetic testimony. It is the earliest chapter of cosmic history that can be carried to us by light. And that is why it feels like a horizon with teeth, because it isn't just far away. It is a barrier in time, a boundary defined by the universe's own physical state. When we say the CMB fills the sky, we mean it literally. It's everywhere. Look in any direction, north, south, anywhere, and beyond the galaxies, beyond the deep infrared glow, beyond the last faint structures, there is the CMB. It's often described as a surface, but it isn't a surface like a planet or a shell. It's a spherical boundary around us, known as the surface of last scattering, the place where the photons we see today last interacted strongly with matter before traveling freely. This surface is not a material object. It is a map of a moment, a snapshot of the universe at around 380,000 years old. And now comes the almost unbelievable part. We have measured it. Not vaguely, not poetically, measured it. Space missions mapped this glow in exquisite detail. NASA's COBE, then WMAP, and later the Planck spacecraft led by ESA. They turned the whole sky into data. They revealed that this ancient light has an average temperature of about 2.7 Kelvin, around minus 270 degrees Celsius, about minus 454 degrees Fahrenheit. That number is so cold it feels like nothing, but it is the cooled remnant of a universe that was once blazing hot. Light that has been stretched by cosmic expansion for nearly 13.8 billion years. The universe didn't lose. Its light, it diluted it, it redshifted it, it cooled it into microwaves. So the CMB is not just old, it is aged by expansion itself. At first glance, the CMB is almost perfectly uniform. This is one of the most unsettling facts in cosmology. Across the entire sky, the temperature is nearly the same. Not exactly, but close enough to raise eyebrows in every generation of scientists who studies it. The variations, the tiny hot and cold spots, are incredibly small, on the order of 1 part in 100,000. That difference is so slight it's almost humiliating. It's like measuring the temperature of an entire planet and discovering that most of it differs by less than the warmth of a breath. And yet those tiny fluctuations are everything, because they are the seeds, the faint imprints of slight density differences in the early universe, regions just a little thicker, a little heavier, where gravity would later pull matter together more strongly. Those tiny imperfections are the blueprint of structure, the reason galaxies formed here and not there, the reason clusters exist, the reason the universe is not a perfectly smooth fog today. So the CMB is both calm and violent, calm in its uniformity, violent in what its tiny deviations imply. It is the universe whispering its earliest unevenness into the sky. And here is the strangest part to feel, personally. Even if you can't see it with your eyes, even if you're standing under city lights, even if the stars are washed out, the CMB is still above your head, right now, passing through you, a sea of ancient photons that left when the cosmos was young, when Earth did not exist, when the sun did not exist, when even the Milky Way was not yet assembled. Those photons have been traveling for nearly the entire age of the universe, and tonight, some of them end their journey in our instruments, in our detectors, in the fragile technology of a species that only recently learned to write. That is, not just science. That is a kind of existential collision between the briefness of human life and the depth of cosmic time. So why can't we see beyond the CMB using light? Because before that era, the universe was not transparent. It was a plasma that scattered photons relentlessly. There is no clean electromagnetic image from earlier times that could survive the trip to us. Not because the information doesn't exist, because it can't travel in the form we rely on. So the CMB becomes the farthest electromagnetic signal we can ever receive directly. A hard limit not imposed by engineering, but by the physics of the early universe. In a way, the CMB is the universe's oldest surviving photograph, not of stars, not of galaxies, but of the primordial conditions that made everything else possible. When we look at the CMB, we are looking at the universe before it had the structures we're used to, before galaxies turned on like lanterns, before star fields became familiar, before the cosmos looked like anything we'd call space. And yet the CMB is not meaningless glow. It is structured, it has a pattern, it has tiny fluctuations that can be measured, mapped, compared, and tested against physical models. It is one of the strongest reasons modern cosmology is not just storytelling, it is evidence. The universe has left us its fingerprint. But then, a colder, more human problem appears. Because if the CMB is the farthest light we can ever see, then the edge we talk about is not a physical border. It's a boundary of what light can reveal. And once we understand that, we have to confront what the edge is not. Because the moment we mistake this horizon for a wall, we start believing the wrong story. A story about endings, a story about emptiness, a story about darkness beyond, and that story is almost always false. There's a temptation that feels almost innocent. When we hear the word edge, we imagine a border, a rim, a last line where space ends and something else begins. Our minds build a picture the way they always have, using oceans, cliffs, walls, horizons on Earth. But the universe punishes that instinct, because the moment we imagine a physical edge, we start believing in things that are not there. A cosmic wall, a shell, a boundary you could fly toward until your engines sputter and the universe simply stops. That story is comforting, and it is almost certainly wrong. If we could travel outward, past galaxies, past the last bright structures, past the faintest detectable glow, there is no evidence we would meet a surface you could touch, no cosmic masonry, no border marked by matter, no place where the laws of physics read, do not enter. Einstein's general relativity does not require an edge. In fact, the mathematics that describes expansion and curvature works perfectly, well without one. A space can be finite and still have no boundary. It can wrap back on itself in ways our intuition can barely hold, or it can be infinite with no outermost place at all. Either way, an edge in the everyday sense is not a feature physics demands. The problem is not that the universe hides a wall. The problem is that our language keeps trying to build one. Imagine this. Picture an old paper map of the world, creased, faded, torn at the edges. The map ends abruptly. At the edge of the paper, the ink stops. But we know what that edge really is. It's not the end of Earth, it's the end of the map. The world continues beyond the paper, because the paper was never the world. It was only our representation of it. That's what the edge of the universe usually is, not an ending in reality, an ending in what we can access, in what we can measure, in what information has reached us so far. Another instinct follows right behind the first. If we can't see, beyond the horizon, we assume what lies beyond must be dark, empty, cold, nothing. But the horizon is not a floodlight fading out. It's a limit of communication, a boundary created by the speed of light and the history of time. The universe does not turn off where our telescopes stop. Our view does, and that difference matters, because beyond the observable region, space could still be filled with galaxies, stars, radiation, matter, obeying the same physics we measure here. Not because we are certain, but because the simplest reading of modern cosmology is that the laws of physics do not suddenly change at the edge of our information. The horizon is not a curtain hiding a void. It is the edge of the messages that have arrived. This is the hardest correction, because it wounds the ego of the human mind. We are used to thinking, if we can't see it, it's not part of our world. But cosmology demands a colder humility. What we observe is not the universe. What we observe is the part of the universe that has had time to affect us. The boundary is not in space, it's in causal contact. That means the observable universe is not a container holding all existence. It's more like a lit circle on a vast dark stage, except the darkness isn't emptiness. It's simply unlit to us because the light has not reached us. So when we ask what lies beyond, we have to be careful, because beyond can mean two very different things, beyond our sight or beyond existence. Science only speaks confidently about the first. Here is the tension that sits at the heart of cosmology. Observation is limited. Existence may not be. We have instruments, NASA telescopes, ESA missions, ground observatories built on mountains and deserts, designed to stretch the boundary of what we can detect. But even perfect instruments cannot outrun the universe's timeline. Even infinite sensitivity cannot collect light that has not had time to arrive. So the observable limit is a real physical limit to knowledge, but it is not, by itself, a claim about the total universe. That distinction is not a technicality. It is the line between science and mythology, because the moment we treat the boundary of observation as the boundary of reality, we start making claims that cannot be tested. And science does not survive on claims, it survives on evidence. Scientists are not allergic to wonder, they are allergic to certainty without proof. Stephen Hawking once spoke often about the universe as something we can describe with laws, even when our imagination fails. But even the most poetic physicist cannot turn an untestable idea into a verified one just by saying it beautifully. Modern cosmology is built on measurements, expansion rates, redshifts, galaxy surveys, the CMB mapped by missions like Planck and earlier NASA probes. Every strong statement is chained to a signal that arrived. So when someone says, beyond the edge is nothing, or beyond the edge is another universe, or beyond the edge is a wall, science asks the same brutal question. What observation could prove that wrong? If there is no answer, it isn't a scientific claim. It may be a story, it may be a philosophy, but it is not evidence-based cosmology, and the universe does not reward us for pretending otherwise. There is another misconception hidden inside our fear of the horizon. We confuse the unknown with the unknowable. Unknown means we don't have the data yet. We may get it later. We may refine measurements. We may build better instruments. We may discover new ways to infer what we cannot directly see. Unknowable means something stronger. It means there is no possible physical interaction that could ever deliver that information to us. And in a universe with horizons, some things may truly be unknowable, not because of human weakness, but because of the causal structure of space-time. That sounds like surrender, but it's actually clarity. It tells us where science can push and where the universe itself draws the boundary. The unsettling truth is that some regions could exist forever outside our causal contact, not beyond space, beyond interaction, and that is not darkness. That is separation. And if we're honest, you can feel your own mind fighting this. You can feel it trying to build a picture anyway, a last line, a final border, a place you could point to and say, that's the end. That need is human. We evolved inside bounded worlds, valleys, shorelines, mountain ranges, the curve of a horizon. But the universe is not obligated to match the shapes our brains find comforting. So the task here isn't to imagine a better wall, it's to accept a more unsettling idea. The edge is not a thing, it's a limit on what can reach us. There is one more misconception that hides underneath all the others. We assume that the universe must behave like a room, that space must be inside something, that outside must exist. But in general relativity, space is not a room, it's part of the phenomenon. Asking what's outside the universe can be like asking what's north of the North Pole. The question feels meaningful because it uses familiar words, but the geometry may not contain what the words imply. That doesn't mean curiosity is wrong, it means our language can mislead us. And when language misleads us, we start chasing ghosts, walls, borders, empty darkness, a literal edge. The universe does not promise any of those. So what can we say, confidently, without crossing the line into untestable certainty? We can say the observable universe is limited by light travel time and the history of cosmic expansion. We can say the horizon is not a physical boundary, but a boundary of causal contact. We can say there is no evidence for a wall, a shell, or a place where physics ends. We can say that darkness beyond the horizon is not implied by the horizon itself, and we can say something else, something simple but heavy. The universe does not end where our knowledge ends, but then a deeper question replaces the one we just dismantled. If there is no wall, if there is no empty darkness, if the horizon is only an information limit, then what is it reasonable to believe about the space beyond our sight? Not fantasy, not speculation dressed as certainty, but the most disciplined, evidence-respecting extension of what we already measure. Because the next mystery isn't about an edge at all. It's about the rest of the universe, quietly existing beyond our reach, obeying the same laws, and waiting, perhaps forever, outside our causal touch. Once we strip away the myths, no wall, no shell, no cosmic cliff, what remains is a quieter, more unsettling truth. The universe doesn't end at the horizon. Our information ends, and beyond that limit, there is a region of reality that may be vast beyond comprehension, yet unreachable to us, not because it's hiding, but because it cannot speak to us yet, or ever. This is where the story becomes delicate, because we are about to talk about what lies outside our observable universe. And science does not allow us to invent, so we have to move with discipline, not with fantasy, not with certainty that outpaces evidence, but with the simplest extension of what we already know. First, we need to disarm a word. Outside makes it sound like a separate place, like another room beyond a door. But beyond the observable universe is not somewhere else. It is the same space, same universe, simply beyond the range of signals that have reached us so far. It's not a different domain. It's the continuation of this domain beyond our current causal reach. If we could somehow stand there, at some point beyond our horizon, nothing magical would happen. No seam in reality, no change of physics, no sign that we crossed a border. Because the border is not in space, it is in communication, in time, in what can reach what. That's why the horizon is so strange. It feels like a boundary, but it's really an information limit. We already know, from the way light works, that there must be regions whose light has not reached us yet. The universe is about 13.8 billion years old. Light travels at a finite speed, and the universe has been expanding the whole time, so there will always be places that are simply too far in terms of time and expansion for their signals to have arrived. This is not speculation, it is a direct consequence of how cosmic horizons work. The observable universe is like a sphere of received history. Beyond it is the rest of the universe that has not yet joined our story through incoming light, and that's when the unease sets in, because we can't help but ask, what is out there? Science can't give a detailed inventory of what we haven't observed, but it can tell us what it is rational to expect, based on evidence inside the observable universe. And here is the key. The universe, on the largest scales we can measure, appears broadly uniform, not in the sense of being identical everywhere. Galaxies cluster, voids yawn open, matter collects and separates. But statistically, on enormous scales, the universe looks roughly the same in all directions. This is what cosmologists refer to when they talk about homogeneity and isotropy. Those words sound abstract, but the idea is simple. When we zoom far enough out, the universe does not look like a special pattern aimed at us. It looks like a cosmos with no privileged direction, no obvious center, no preferred orientation, and that matters, because if the universe looks broadly the same in every direction from here, then the simplest extension is that it continues to look broadly the same beyond our horizon. Not because we can prove it, but because that is the most conservative assumption consistent with what we observe. And scientists prefer conservative assumptions, because the alternative is to invent without evidence. Imagine this. You're standing in a vast field on a foggy morning. You can see only as far as the fog allows, maybe a few dozen meters. Within that circle of visibility, you see grass, a few trees, and a fence in the distance. Now you cannot see beyond the fog, but the fog is not a wall, it's a visibility limit. So when you ask, what's beyond what I can see? The most rational answer is, probably more field, probably more trees, probably the continuation of the landscape you're already standing in. Could it change dramatically beyond the fog? Yes, but without evidence it's not scientific. To declare it does. The observable universe is like that, not because fog is the same as light travel time, but because the logic is the same. A limit of sight is not evidence of an ending, it is only evidence of a limit. Now we reach a critical point. When we say regions beyond our horizon likely obey the same physical laws, that is not just comfort, it is grounded in how physics works. The laws we measure, gravity described by general relativity, the behavior of atoms described by quantum mechanics, the way light interacts with matter, have been tested across the observable universe. We see the same atomic fingerprints in the light from distant galaxies, the same spectral lines, the same basic chemistry, the same gravitational behavior shaping clusters and bending light. This consistency across billions of light years suggests that physics is not a local custom, it's not a regional dialect, it behaves as a law. So unless we have evidence otherwise, the disciplined move is to assume the same laws apply beyond our horizon. not as a claim of certainty, as a refusal to invent new physics without necessity. That is how science stays honest. Here's where the distinction matters. There is a difference between making something up and extending what we already observe beyond the edge of our data. If we observe uniformity on large scales in every direction we can see, then the simplest continuation is that the universe beyond our horizon is not radically different. If we observe that the laws of physics appear consistent across the observable cosmos, then the simplest continuation is that those laws don't suddenly change beyond the reach of our telescopes. This is not storytelling. It is the same reasoning we use everywhere in science. We assume consistency unless there is evidence of a boundary that breaks it, and so far, we have no evidence of such a boundary. Not in the distribution of galaxies, not in the physics encoded in light, not in the behavior of space-time on the largest scales we can measure. So we don't get to declare a cosmic surprise beyond the horizon. We get to say something more cautious and more profound. Beyond our horizon is likely more universe. There's a psychological trick our minds play on us. We treat beyond like a separate realm, but the universe beyond our observable limit is not elsewhere. It is not a different universe. It is the continuation of this one. The difference is not in location, it's in connectivity. The horizon is not a wall dividing reality into two different places. It is a boundary dividing reality into what can exchange information with us and what cannot, at least not yet. And this is where the story becomes existential, because it means there can be galaxies, real galaxies, with real stars and real planets that will never be part of our sky. Not because they're hidden, because the universe's causal structure forbids contact. They are not far away in the way a mountain is far away. They are far away in the way the past is far away. They exist beyond the reach of our timeline, and if you sit with that for a moment, you feel the quiet weight of it. You are living inside a cosmos that may be vastly larger than anything you can ever know directly. Not because you are small, not because our technology is weak, but because physics itself draws a boundary around your knowledge, around all possible knowledge from this location. That boundary isn't cruel, it isn't personal, it's simply what happens when light has a finite speed and the universe has a finite history. We are inside a partial view of something potentially far greater, and there is no shame in that. There is only honesty. Now, we arrive at one last misconception that quietly poisons this entire topic. When people hear we don't know what's beyond, they often translate that into there's nothing there, or it's just empty. But that's an error. The absence of data is not evidence of absence. It's only evidence that we haven't received the data. The universe does not become empty just because we can't observe it, and the cosmos is filled with structures so large they already challenge our imagination. Filaments of galaxies, vast voids, clusters bound by gravity. It would be strange, given what we see, to assume structure abruptly stops right beyond the range of our sight. Not impossible, but unsupported. The responsible stance is not nothing, it is unknown but likely continuous. And that's a very different kind of humility. So what exists beyond the observable universe? We cannot list galaxies by name. We cannot map those regions with light we haven't received. But we can say, with disciplined confidence, there are regions of space beyond our horizon simply because of how light, time, and expansion work. Those regions are not elsewhere. They are part of this universe, just outside our causal reach. And based on what we observe within our horizon, large-scale uniformity and consistent physical laws, the simplest extension is that those regions likely contain more of the same kind of universe: matter, radiation, structure, and evolution. Not fantasy, not certainty, the most conservative continuation of evidence. But then, the universe delivers another twist. because even this calm picture assumes a horizon that stays put, a boundary that slowly grows as time passes. Except the universe is not only expanding, it's accelerating. And acceleration changes the meaning of unreachable. It turns not yet into never. It turns a horizon of the past into a horizon of the future. And once we face that, we realize something truly disturbing. There are galaxies we can see today that are already slipping beyond all future contact, forever. For most of human history, we carried a quiet assumption that the universe is expanding, yes, but slowing down, because gravity should be doing what gravity always does, pulling, braking, dragging everything back, a cosmic expansion with a built-in resistance, a universe that stretches but grows tired. Then the evidence arrived, and it didn't just challenge that assumption, it shattered it. Because the universe isn't slowing down, it's speeding up, and once we accept that, the edge stops being a passive limit of sight and becomes something far more disturbing, a boundary that can move away from us faster than we can ever chase it. In the late 1990s, two independent teams studying distant Type 1, a supernovae, found something that didn't fit the expected script. The Supernova Cosmology Project and the High-Z Supernova Search Team were using these supernovae as standard candles, explosions with predictable intrinsic brightness, so their apparent dimness could be used to estimate distance. They were trying to measure how the expansion of the universe changed over time. They expected to see deceleration. They expected gravity's fingerprints. Instead, they found that distant supernovae were dimmer than they should be in a slowing universe. The simplest explanation was also the most unsettling. The expansion has been accelerating, and it wasn't a small correction. It was a fundamental change in our cosmic story. So profound that, in 2011, the Nobel Prize in Physics was awarded for this discovery. But the prize didn't solve the mystery. It only confirmed the wound. Imagine this. Picture we're in a car at night on an empty road. At first, we accelerate normally, then we take our foot off the gas. We expect the car to gradually slow, but instead, the speedometer climbs, faster and faster. No engine roar, no visible push, just increasing speed with no obvious cause. That's what the accelerating universe feels like. Gravity should slow the expansion, but the data says the expansion is picking up pace. Something is acting like a pressure built into space itself, something that overwhelms gravity on the largest scales. Type 1. A supernovae are not just bright, they are monstrously bright. So bright we can detect them across billions of light years. And because their brightness can be standardized, they become a measuring stick for cosmic history. When astronomers compared how bright these explosions appeared at different redshifts, they weren't just looking at fireworks. They were looking at the universe's expansion written into light. The conclusion wasn't based on a single observation. It was a pattern seen across many supernovae by independent teams, then later supported by other lines of evidence, like the cosmic microwave background and large-scale structure surveys, multiple cosmic witnesses pointing to the same claim. Acceleration is real, but then the real problem appeared. To describe what could cause acceleration, cosmologists use a name that sounds like an answer, even though it isn't. Dark energy. It's not dark because it's a shadowy substance we've photographed. It's dark because we don't see it directly. We infer it from its effect on expansion. We measure its influence through the way space evolves, through how distances grow, through how structure forms, through how the CMB encodes the universe's geometry. So dark energy is a measured component in our best models, but its nature, what it physically is, remains one of the deepest open questions in physics. This is why the story stays tense. We have evidence of acceleration. We have a name for the driver, but the driver's identity is still unknown, and the consequences are not philosophical. They are geometric. They reshape what beyond the edge even means. Up to now, we've been living with one kind of boundary, a limit based on the universe's age, the particle horizon. That's the farthest distance from which light has had time to reach us since the beginning. But acceleration introduces another boundary, one that looks forward, not backward. A boundary tied not to the past we can see, but to the future we can ever contact. This is called the cosmic event horizon, and it is one of the most disturbing ideas in modern cosmology, because it means there are regions of the universe that can send us light today, but will never be able to send us light in the far future. Not because they die, because space itself expands in a way that prevents their signals from ever catching up. The universe doesn't just limit what we can see now, it can limit what we can ever see, no matter how long we wait. We can feel the difference like this. The particle horizon is a record of what has already had time to reach us. It grows as the universe ages, because more time allows more signals to arrive. The event horizon is a boundary on future. Contact. It answers a colder question. What can we ever interact with, even in principle, if the universe continues to accelerate? In an accelerating universe, there are regions whose light will never reach us after a certain time. They are not outside the universe. They are outside our future, outside the reachable network of cause and effect that includes us. And that changes the emotional texture of the edge, because now the edge isn't only the limit of our past light, it's the limit of our cosmic future. Here's where the universe plays its most confusing trick. We can observe galaxies so distant that their recession speed, due to expansion, exceeds the speed of light. That sounds like a violation, but it isn't, because nothing is locally moving through space faster than light in its immediate neighborhood. Instead, the space between us and those galaxies is increasing so rapidly that the distance grows faster than light can close it. It's like trying to swim toward a shore while the river widens beneath you. No matter how strong the swimmer is, the geometry wins, and in an accelerating universe, that river widening can become permanent. Some galaxies are already on trajectories where, even if we waited forever, their future light will never arrive. They are visible now only because we're receiving photons that left long ago, when the universe's scale was different. We are watching the last messages of regions that are slipping away, and if you want to feel the weight of that, take a breath and look up, mentally, beyond the ceiling, beyond the city, beyond the atmosphere. Some of the galaxies we can detect are, in a sense, already gone from our future. You are seeing them because their ancient light is still arriving. But the universe is stretching so relentlessly that, over unimaginable time, those galaxies will fade. Not because they stop existing, but because their new light can no longer reach us. It's not that they fall off an edge, it's that the cosmic network of contact breaks, quietly, legally, by the rules of space-time. This is one of the most haunting implications of cosmic acceleration. If dark energy continues to dominate expansion, the observable universe of the far future becomes lonelier. Galaxies beyond our local gravitational neighborhood will recede farther and farther. Their light will redshift more severely. Their signals will thin, and over deep time, much of the large-scale universe will become undetectable to observers like us. Future astronomers, if any exist, could look out and see a sky with fewer galaxies, less evidence, less cosmic history on display, not because the universe shrank, but because the universe expanded in a way that hid its own vastness. This isn't just poetic, it's a physical consequence of acceleration. It can erase accessible information. It can turn a richly populated cosmos into an observational island. And that creates a darker tension, because it means our era, right now, may be unusually fortunate. We live at a time when the universe still shows us its deep structure, a time when distant galaxies still speak to us. But the universe will not always be this generous. So what exactly is dark energy doing? In the simplest terms, it behaves like a property of space that doesn't thin away as the universe expands. So as there is more space, there is more of whatever is driving the acceleration. That sentence is dangerous if we treat it like certainty about the underlying substance. We don't know the substance, but we do measure the effect. We see the expansion history, we see the geometry, we see the accelerated stretching. And when we put those measurements together, the cosmos points toward a component with negative pressure-like behavior, something that pushes the expansion to speed up. We can measure its influence. We can estimate how much of the total cosmic energy budget it represents in the standard model. But the fundamental "what is it?" remains open, and that open question is not a weakness. It's the engine of the mystery. So the edge is pulling away, not as a wall in space, as a moving boundary in causality. Acceleration takes the cosmic horizon and gives it teeth. There are parts of the universe that are not just beyond us now, they are beyond all future reach. And suddenly, what lies beyond the edge stops being a question about geography. It becomes a question about information, about what can ever influence what, about what it means for something to exist and yet be forever disconnected from us. And that raises a deeper, colder question, one we can't avoid anymore. If the universe can hide entire regions behind horizons, then what is a horizon really? Not as a poetic limit, as a fundamental constraint on information, causality, and physical law. Because once we see the universe accelerating, we realize the true boundary isn't distance, it's communication. And the universe is built from what can reach what, nothing more and nothing less. At some point, the edge stops being a question about distance and becomes a question about law, because when cosmologists talk about horizons, they are not talking about walls. They are talking about something far colder, a limit on causality, a limit on influence, a limit on what can ever reach what. And once we accept that, we realize the universe isn't defined by what exists out there. It's defined by what can touch what, even with nothing but a whisper of light. Because in physics, existence is not only about being, it's about interaction. Causality is the rule that makes the universe behave like a story with structure, cause, then effect, not reversed, not scrambled, not arriving before it's sent. Without causality, science collapses, because experiments would stop meaning anything. A measurement would no longer connect to the event that produced it. Time would become noise. So in every serious physical theory, from Einstein's relativity to quantum field theory, causality sits underneath everything like bedrock. Relativity, in particular, gives causality a shape, not a metaphorical shape, a geometric one, a structure woven into space-time, a structure that tells us which events can influence which other events. And that structure is not negotiable. The speed of light is not just how fast light goes, it's the speed limit for information, for cause and effect, for any influence that could connect two events across space. When Einstein built general relativity, he didn't just change gravity, he changed the meaning of simultaneity. He showed that time and space are braided together, and that no signal can outrun the fundamental causal structure. If something could transmit information faster than light, causality would fracture, because in some reference frames that would allow effects to appear before causes. It would allow paradoxes that don't just confuse philosophers, they break the machinery of physics. So the universe enforces a limit, not because it's cruel, because it must, because without that limit reality would be internally inconsistent, and from that single constraint, horizons become inevitable. Imagine this. Picture we're in a huge city at night. There's a strict rule. No message, no sound. No signal can travel faster than a specific speed. Now imagine the city is expanding, streets lengthening, buildings drifting apart, distance is growing. Even if the speed limit stays the same, the expanding city creates regions that messages can never reach in time. Not because there's a wall, because the distance grows faster than communication can cross it. That's what cosmic horizons are. Not barriers in space, barriers in reach, barriers in time, barriers built from a speed limit combined with an expanding arena. This is the deepest correction to the word edge. A horizon is not an edge of space, it is an edge of information. When we say there's a cosmic horizon, we mean there are events beyond which signals have not reached us. Or, in the case of an event horizon, in an accelerating universe, signals will never reach us, no matter how long we wait. So the horizon is not about where the universe ends, it's about where our causal contact ends. And that is a very different kind of boundary. It doesn't separate reality into exists and doesn't exist. It separates reality into can affect us and cannot. The universe remains continuous, but our access to it is not. Here's where the story becomes almost philosophical, except it's forced on us by physics. If there are regions of the universe forever beyond our causal contact, what does it mean for them to exist for us? This is not a trick question. It's not wordplay. It's an honest consequence of horizons. Those regions can have galaxies, stars, planets, radiation. They can be real. They can evolve. But if no information from them can ever reach us, and no influence from us can ever reach them, then they are not part of our physical story in any operational sense. They are disconnected. Not elsewhere. Disconnected. It's like two books written in the same language, using the same laws of grammar, but sealed in separate vaults forever. They can both exist, but they can never exchange a sentence. In cosmology, horizons create that kind of separation, and the separation is not psychological, it is geometrical. So instead of imagining the universe as a map of places, it can be more honest to imagine it as a network of connections. What can influence what? What can send information to what? What regions share causal contact? In this view, our universe, the universe that matters to us physically, is the set of events that lie within our causal past and causal future. Everything that can affect us, everything we can affect, everything connected by possible signals, even if those signals take billions of years. That network is what physics can speak about, because physics is built from interactions, measurements, signals, fields, forces. Every law we know is revealed through connection, and horizons slice the network. They cut potential links, they limit the graph of cause and effect, and suddenly the edge is not about distance, it's about a broken chain. And this is where you can feel how strange your own existence is. When you look into the night sky, you are not seeing space. You are reading messages, photons that left their sources long ago, signals that traveled for millions, even billions of years, just to arrive here, now, inside your eyes, or inside our detectors. You are standing inside a stream of information from the past. And beyond a certain boundary, there are no messages, not because nothing happened, because nothing could reach you. The sky is not a picture, it's a causal archive, and it has a limit. This is why science avoids untestable claims about regions forever beyond. Contact, because if there is no possible interaction, there is no experiment, no measurement, no way to tie a theory to evidence. Physics doesn't deny that disconnected regions could exist, but it can't treat them the same way it treats things that can leave traces in our instruments. Physics is defined by what can influence what. That's not a limitation of imagination. It's the discipline that separates knowledge from invention, and horizons are the universe enforcing that discipline on us. They are telling us, here is where evidence can arrive, and here is where it cannot. So the deepest meaning of cosmic boundaries is not, here's the end. It's, Here's where the rules of causality stop allowing communication. So now, the edge becomes something sharper, not a distant region, a law of connectivity, a boundary drawn by light speed, time, and the expansion of space-time. And once we see the universe that way, another temptation appears, one that feels heroic. If horizons block information, can we overcome them by traveling? Can we chase the boundary with technology? Can we outrun the universe's own geometry? It sounds like an engineering problem. It sounds like a future civilization challenge. But the universe doesn't treat it that way, because the barrier is not about our engines. It's about the structure of space-time itself. And the next question is not, what's out there? The next question is, can we ever go beyond, even in principle? There is a reflex in us that refuses to accept limits. If the universe places a horizon in front of us, we immediately imagine an answer that feels almost heroic. We will build faster ships. We will stretch our reach. We will go, because we are a species that turns distance into a challenge. But then, the universe delivers a colder truth. Cosmic horizons are not fences we can climb. They are not borders we can cross with better engineering. They are consequences of space-time itself. And that means the question isn't really, can we travel far enough? The question is, can motion through space ever defeat the geometry of the universe? We need to separate two ideas that our instincts keep blending together. One is motion through space, a rocket, a probe, a beam of light. The other is the expansion of space, the way distances between faraway regions can grow because space-time itself is stretching. Those are not the same thing. A rocket has a speed through space. Expansion is space itself changing. And the universe doesn't care how advanced our engines are if the underlying geometry is moving the destination away faster than any signal can close the gap. This is why the horizon is so unforgiving. It's not just far, it's not reachable, in the same way yesterday is not reachable. Special relativity, Einstein's first revolution, sets a hard causal limit. No information, no physical influence, no message can outrun light in a vacuum. That is not a technological limit. It's not, we haven't figured it out yet. It's built into the structure of cause and effect. Light moves at about 300,000 kilometers per second, roughly 186,000 miles per second, and we can feel how absurdly fast that is. At that speed, a flash of light can circle Earth more than 7 times in a single second. And even that, this almost divine speed, does not let us outrun a cosmic horizon. Because the horizon is not a race against distance alone, it's a race against time and expanding geometry. Imagine this. Picture we're trying to run up an escalator that's moving down. At first, we can make progress. We run, we gain steps, we climb. But if the escalator speeds up, there comes a moment where no matter how hard we run, we stop gaining ground. And if it speeds up even more, we start sliding backward. Not because we got weaker, because the moving surface became stronger than our motion. That's the logic of an event horizon in an accelerating universe. We can move through space, we can travel, we can even go far. But if the fabric of space between us and a destination is stretching in the wrong way, the destination can become unreachable, not just practically, but fundamentally. A common escape fantasy sounds reasonable at first. If the horizon is about light, then we'll go faster than light. But faster than light travel is not just hard, it breaks causality and relativity. It breaks the ordering of events. It allows effects to arrive before causes in some frames of reference. And when causality fractures, physics stops being a coherent system. So, if we stay within established verified physics, faster than light travel is not a tool we can assume, which leaves us with the speed limit we already have, and that means the horizon remains what it is, a limit on influence, not a limit on ambition. Here is the uncomfortable core. In an expanding universe, distant galaxies are not merely moving away. The distance between us and them is increasing because the space between us is stretching. If that stretching becomes strong enough over large distances, then even a beam of light aimed outward can fail to ever reach certain regions. Not because light slows down, because the distance it must cross keeps growing. This is the difference between driving to a city and trying to reach a shoreline while the ocean widens faster than you can swim. The universe doesn't need to build a wall, it only needs to stretch, and the stretching itself becomes the barrier. So what does this mean for exploration? It means there are, in principle, regions we can never visit. Not because we are fragile creatures, not because our civilization will collapse, but because even if we had a perfect ship, one that could travel arbitrarily close to the speed of light, cosmic horizons still define an ultimate boundary. We could spend a lifetime accelerating, crossing interstellar space, reaching other stars, perhaps even other galaxies in our local group. But there exist regions so far and so causally disconnected by expansion that no trajectory staying within light speed limits can ever reach them. This isn't pessimism, it's geometry. But exploration is only one side of the human hunger. The other is measurement. We might accept that we can't go somewhere, and still hope we can know it. So we imagine other probes, signals, tricks, new messengers. And yes, we can extend knowledge beyond visible light. We already do. We use radio waves, infrared, X-rays, gamma rays. We use cosmic messengers like neutrinos and gravitational waves. But here is the harsh continuity. Even those messengers are still limited by causality. They cannot outrun the structure of space-time. They cannot carry information from beyond a horizon that is defined as no influence can reach us. A horizon is not a limit of telescopes. It's a limit of the universe's ability to deliver information to our location. So no detector, no matter how perfect, can measure what cannot arrive. The universe doesn't hide the data behind a curtain. It simply does not permit the data to cross. Now, we can still do something powerful. We can build theories. We can test them against what we observe. We can infer what must be true about regions we cannot directly sample based on consistency and physical law. That's not fantasy, that's science. But it comes with a discipline that is almost painful. A theory without possible observational consequences is not physics in the strict sense. It might be mathematics, it might be philosophy, it might even be beautiful. But physics, real, grounded physics, requires that a claim can, at least in principle, be connected to evidence. And cosmic horizons sever those connections. They limit what the universe will ever allow us to confirm. It's tempting to push the problem into the future, to imagine that 1,000,000 years from now, a civilization could brute force its way past these limits. But those limits are not about our current weakness. They are about the rules of space-time. If causality is built into the universe, then any intelligence living inside this universe inherits the same constraints. They can compute more, they can build bigger, they can live longer. But they cannot send information faster than light without tearing causality, and they cannot make a horizon vanish if the universe's expansion creates it. This is one of the most sobering thoughts in cosmology. The universe sets boundaries that no intelligence can cross, not because it is hostile, but because it is consistent. And if you feel a kind of grief in that, you're not imagining it. Because we are used to thinking that every mystery is temporary, that if we work long enough, we will eventually know. But a horizon is the universe refusing a question, not out of malice, out of structure. It's the cosmos saying, from where you stand, there are things you can never touch and never be touched by. And that is not an insult to our intelligence. It's a reminder of what intelligence is. A system that learns by connection. So where does that leave us? It leaves us with a distinction that matters more than any rocket blueprint. Technology can overcome obstacles inside the rules. Better sensors can see fainter signals. Bigger telescopes can collect older photons. Smarter algorithms can extract patterns from noise. But technology cannot rewrite the foundational laws without evidence that those laws are wrong. And so far, the evidence points the other way. Relativity has survived every serious test in its domain. Causality holds. The speed limit holds. Horizons emerge naturally from these rules in an evolving universe. So if we are honest, we have to say, the edge is not a challenge for our machines. It is a feature of reality. And now we arrive at the most unsettling realization. When we ask, can we ever go beyond? We are still imagining an edge like a place, a location we can reach, a line we can cross. But the boundary we've been circling is not a line in space. It's a limit in the way space-time connects events. So, beyond may not mean what our instincts want it to mean. Maybe the universe doesn't have an edge in the ordinary sense at all. Maybe it never offered a border. To cross, only a horizon to interpret. And that creates a new problem, deeper than travel, deeper than measurement. If the edge is not a place, then what kind of universe are we actually living in? One with a boundary? Or one where the very idea of beyond is an illusion created by perception and causality? We keep asking it like it's a place, like there's a final ridge of galaxies, a last lantern, and then a hard line where the universe stops. But then, the deeper we look, the more the question itself begins to fracture, because the universe does not behave like a room, it behaves like geometry. And geometry doesn't end the way walls end. It curves, it loops, it stretches. It can be finite without having an edge. It can be endless without being a place you can point to. And that's where the story turns strange in a quieter way. Not with explosions, not with monsters, but with a single, unsettling possibility. Maybe beyond the edge is a question built from human instinct, not from the universe. Beyond is a word we learned on Earth. Beyond the hill, beyond the ocean, beyond the city limits. On Earth, beyond usually means there's more space if we keep moving. But the universe is not obligated to honor our language. Because in cosmology, space is not a container. It's the thing being described. It's the very fabric whose shape we're trying to understand. And this is where everything changes. If space itself has a global shape, if it has an overall geometry, then it can be finite without having a boundary you could ever reach. It can be like the surface of Earth, finite area, no edge. You can travel forever and never fall off. Not because there's a wall, because the concept of off doesn't exist on the surface. That doesn't prove the universe works that way, but it shows something crucial. An edge is not required for something to be finite, and a horizon is not evidence of an edge. It's evidence of a limit in information. Imagine this. Picture you're walking in a straight line across a perfectly smooth planet. No oceans, no mountains, no borders, just ground beneath your feet. You never turn, you never stop, you keep going. And at first it feels like you must eventually reach a boundary, because that's what our instincts expect. But hours pass, then days, then months, and one morning you see something impossible on the horizon. Your own footprints, not because you circled back intentionally, because the space you were walking on is closed, finite, edgeless. That's the idea cosmology forces us to consider. Space can be all there is and still not have an edge. Now comes the disciplined part, the part that science insists on. Do we know whether the universe is finite or infinite? No, we do not. But we are not blind either. We have constraints, we have measurements, we have evidence that narrows what is plausible. Cosmologists look for the large-scale geometry of space by studying how light travels across the cosmos, how patterns appear in the cosmic microwave background, how galaxies distribute across immense distances, how expansion unfolds over time. Missions like NASA's WMAP and the ESA's Planck satellite mapped the ancient afterglow of the universe, with staggering precision, measuring tiny variations that act like a cosmic ruler. And what those measurements tell us, again and again, is that the observable universe is consistent with being spatially flat, within the limits of what we can measure. Flat does not automatically mean infinite. Flat could still be finite depending on topology, on how space is connected globally. But consistent with flat means something emotionally important. As far as our best evidence can see, the universe is not strongly curved like a small, closed sphere. If there is curvature, it is subtle, so we stand in a strange in-between. We cannot declare infinity. We cannot declare finitude. We can only say the universe appears remarkably close to geometrically flat across the region we can observe, and that uncertainty is not a weakness. It's honesty under pressure. If space is infinite, there may be no beyond in the ordinary sense, because beyond implies an outside, and an infinite space has no outside. It is not embedded in a larger empty room. It is the room. But if space is finite and edgeless, beyond may still not exist, because the whole concept of beyond relies on boundaries, and an edgeless finite space has none. In both cases, finite without edge or infinite without end, our everyday idea of an edge dissolves. What remains is not a location. What remains is perspective, a horizon, a limit of knowledge. And this is where the word edge becomes what it truly is, a psychological artifact, a consequence of being creatures who evolved inside small landscapes with real borders. Our brains are built to navigate, to survive, to find food, shelter, safety. We are pattern machines optimized for forests, rivers, walls. So when we face the cosmos, we keep trying to force it into familiar shapes. We imagine a center. We imagine an outside. We imagine a line where reality stops. But the universe keeps refusing those intuitions. It keeps replacing them with something colder and more beautiful: geometry, relativity, causality, a horizon that is not a border of existence but a border of access. This is why the edge feels real even when it isn't, because our senses interpret what we can't see as what isn't there. But in cosmology, what we can't see often means only one thing: information has not had time or will never have the ability to reach us. There's a reason cosmologists speak carefully. It's not because they lack imagination, it's because they are surrounded by a universe that punishes arrogance. In a laboratory, we can isolate variables, we can repeat experiments, we can control conditions. But in cosmology, we are inside the experiment. We have one universe, one viewpoint, one sky, and we have to infer the global from the local, the whole from the visible, the deep shape of reality from a limited set of signals arriving at one small world. So science does what it always does when it approaches a boundary. It tightens its language. It separates what is measured from what is suggested. It avoids claims that cannot, even in principle, be tested. Not because the untestable is meaningless, but because physics is built from evidence, and evidence requires contact. And this is the moment you might feel something shift inside you, because we want the universe to give us a final answer, finite or infinite, edge or no edge, a clean conclusion. But the universe doesn't owe us closure. What it offers instead is something rarer, a map of what can be known, and where knowing breaks. That boundary is not a failure. It's a feature of being a mind inside space-time, and when we accept that, the question changes shape. It becomes less like a conquest and more like a stance, a way of standing in front of the unknown without lying to ourselves. Science can tell us extraordinary things. It can tell us the universe has been expanding for billions of years. It can tell us the age of the cosmos is about 13.8 billion years. It can tell us that the observable universe spans roughly 93 billion light-years in diameter, because expansion stretches what light can reach. It can tell us that space is close to flat on the largest scales we can measure. It can tell us that horizons limit our causal contact. But science cannot currently tell us the global topology of all space. It cannot confirm whether the universe is infinite. It cannot guarantee whether the cosmos wraps back on itself in some grand, hidden way. And it cannot answer questions that are defined to have no observational consequences. That's not surrender. That's the boundary line between knowledge and invention, between what we can support and what we can only imagine. So where does that leave the original mystery? What lies beyond the edge of the universe? It leaves us with a quiet reversal. The edge was never a place we could reach. It was never a wall we could touch. It was never waiting at the end of a cosmic journey like a final continent. The edge is what happens when a finite speed of information meets a universe with a finite age, inside a space-time that expands. It is a limit of sight, a limit of contact, a limit of what can ever be part of our evidence. And once we see that, a deeper realization arrives, one that feels almost personal. If the universe may have no edge at all, then the real question is not where the boundary is. The real question is what it means to stand inside a universe where knowledge has horizons, not as a defeat, as a condition of existence. And now, there's only one honest place left to stand, right at that boundary of knowing, where the cosmos is still real, still lawful, still immense, and we are simply here, facing it. There is a moment, quiet, almost embarrassing, when we realize what we've been doing. We've been picturing the universe like a room, a floor, a ceiling, a far wall where everything finally stops. But the universe refuses that picture, because the edge we keep imagining is not a location. It's not a cliff in space. It's not a last streetlight where reality runs out. It's a boundary in knowledge, a boundary carved by a simple, brutal rule. Information takes time to travel. Light is fast, unimaginably fast, but it is not infinite, and the universe has not existed forever. So even in a cosmos filled with galaxies, filled with motion, filled with history, there will always be regions whose messages have never reached us. Not because they aren't real, but because they are causally disconnected from us for now. That is what the horizon actually is. Not an edge of existence, an edge of contact. And once we understand that, the question changes. It stops being, what's at the edge, and becomes, what does it mean to live inside a universe where knowing has limits? Our minds are wired to fill darkness with creatures, to treat the unseen like a threat. So when we hear, beyond the observable universe, some part of us expects something unnatural out there, something waiting. But the honest answer is calmer than fear. Beyond what we can observe, there is more space, more cosmos, not a special zone, not an outside room, just regions whose light has not reached us. And here's the strange part. When cosmologists talk about what lies beyond our horizon, they don't do it like storytellers guessing the ending. They do it like geographers mapping a coastline from the shape of waves and the logic of continuity. We look out and see that, on large scales, the universe is astonishingly uniform. Galaxies and matter spread out in a pattern that looks the same in every direction. When we zoom out far enough, that doesn't prove what's beyond, but it gives us a grounded, cautious expectation. The laws of physics we measure here are not likely to suddenly change just because our light can't reach. So beyond our sight, the simplest extension is not mystery objects. It's more of the same kind of universe, structured, lawful, and indifferent to our desire for drama. And yet, that simplicity is not comforting. It's heavier, because it means the cosmos is not performing for us. It just is. The horizon is often described like a limit that blocks us, But it also gives us something profound, a way to read time, because the farther we look, the older the light we receive. Distance becomes a kind of fossil record, and at the farthest electromagnetic boundary we can access, we meet the cosmic microwave background, the afterglow from the time when the universe cooled enough for light to move freely through space. That faint radiation isn't just old, it's a snapshot of the early universe's conditions, temperature, density patterns, tiny variations that later grew into galaxies and clusters. So the boundary doesn't just say, stop, it says, here is how the story began to become visible. This is why the horizon matters. It is not merely a limitation, it is evidence. It is the universe leaving clues in the only way it can, through signals traveling across time. And when we measure those signals carefully, through instruments built by NASA, by ESA, by teams across universities and observatories, we don't just learn facts, we learn the shape of what is possible. We learn which questions are physical and which questions are psychological. There's a quiet relief in the fact that the universe is intelligible. Not completely, not fully, but enough. General relativity gives us a language for space and time. Observations give us numbers. The universe is about 13.8 billion years old. The observable region spans roughly 93 billion light-years across when we talk about distances now, stretched by expansion. Those numbers are so large they can feel meaningless, so we have to translate them into something our bodies can understand. A light-year is what light covers in 1 year, about 9.5 trillion kilometers, around 5.9 trillion miles. Now multiply that by billions. Our brains don't see that, they shut down, and that's part of the human condition. We evolve for forests and storms, not for cosmic scale. But the universe doesn't require our intuition, it only requires our patience, our instruments, our honesty, and our willingness to accept that some truths feel emotionally impossible at first. Imagine this. Picture yourself standing at a shoreline at night. No waves, no ocean. Just a flat, silent plain that fades into darkness. You hold a small light in your hand, a flashlight. You point it outward, and the beam cuts a narrow tunnel into the black. For a moment it feels like the darkness begins where your light ends, as if the world stops there. But you already know the truth. The landscape doesn't end at the edge of the beam. Only your vision does. The horizon of your flashlight is not the boundary of the world. It's the boundary of what your light can reach. That is what our cosmic horizon is like. Not perfect, not literal, but emotionally accurate. A limit defined by propagation, by travel time, by the finite speed of information. And once we accept that, the darkness stops being a threat. It becomes a statement about physics. And if you let yourself feel it, you'll notice something unsettling. The universe contains places you will never influence, and places that will never influence you. Not because of technology, not because we weren't clever enough, but because the structure of space-time itself can separate regions so completely that no signal can cross. That is not a tragedy of engineering, it's a law of nature, and it forces a deeper kind of humility, because it means reality is larger than a relationship. There can be existence without interaction. There can be galaxies whose light will never touch our eyes, no matter how long we wait. Not because they are hidden, but because the universe is expanding and time has direction. And still, those galaxies do not become mythical. They remain physical. They remain part of the same cosmos. They simply remain outside the circle of our causal life. Some people need the universe to be infinite to feel wonder, but wonder does not come from endlessness. Wonder comes from clarity, from realizing that even the part we can observe already contains more structure and time than any human mind was designed to hold. We live on a planet that has existed for about 4.5 billion years, already a number that swallows civilizations whole. And yet, Earth is young compared to the universe. Our entire history, every empire, every language, every heartbreak fits into a thin film on the surface of a single world, orbiting a star in one galaxy among hundreds of billions, not to diminish us, to locate us, because meaning doesn't evaporate in vastness. It sharpens, it becomes more deliberate, more precious, because we recognize how rare it is for matter to become aware of matter, how rare it is for the universe to look back at itself. There is a fact, simple and staggering, that can hold everything together. Every atom in our bodies was forged in earlier generations of stars. The carbon in our cells, the oxygen we breathe, the iron in our blood. These elements were built in cosmic furnaces and scattered through space by ancient stellar deaths. Long before Earth had continents, long before the sun even existed, matter was already moving, mixing, crossing distances that no organism could survive, not with intention, not with desire, with gravity, with time, with physics. So when we ask what lies beyond our horizon, part of what we're really asking is, how did any of this ever reach here? How did a universe that began hot and dense become a universe with calm skies and thinking minds? The horizon, the background glow, the expansion, all of it is not just abstract cosmology. It is ancestry. It is the story of how conditions became possible for us. So here we are, standing at the horizon, not like explorers facing a wall, but like listeners pressing an ear against the deepest silence nature can produce. And the silence answers, not with emptiness, but with limits. The edge is not a place. It is the boundary of what can ever reach us. Beyond the observable universe is not a realm of special things. It is simply more universe, likely governed by the same laws, continuing beyond our sight. The boundary is not a defeat. It is a tool. It tells us how the universe began to become transparent, how it expanded, how structure formed, how time and space braided themselves into the reality we inhabit. And in the end, the most human truth is almost painfully simple. To ask what lies beyond is to recognize our place within, not at the center, not at the end, but inside a vast, lawful cosmos, where even a small world can produce a mind that dares to look outward, and that, in the cold scale of the universe, is not small at all. It is astonishing, quietly, unimaginably true.